All right, so now we're going to look at other ways we can return objects. So if you recall, the first time we wrote this odds ratio function, we just returned this character string expression here that prints out the odds ratio and the confidence interval associated with it. But there are different ways to return objects. For example, we could just type OR at the very end, and then when you call the odds ratio function and store it in an object, the thing that gets printed automatically is just that sample estimate for OR. We could also use return OR, which would really be equivalent to just printing OR here. Invisible OR would make that also the returned object, except would not by default print it out. Finally, we could do something a little bit more appropriate for this case where we want a list object that summarizes all of the main computational results. So here we could create a list object called out that would provide the sample odds ratio, the confidence limits, and the confidence level. And then we could run the function return out. Notice that these are all commented out. So if you wanted to actually have the out function returned, we'd need to not have these hashtags out in front. So with unassigned or assigned function results, we could just run odds ratio and make a prediction real quick. If we just ran odds ratio as it appears right up here, what would we see? And then we could assign odds ratios to an object OR, and what would be contained in that function, okay? So take a look, make sure you understand why we see more output here, given we have this cat expression, and less output here in this object OR, and how the play of the OR returned object versus the print expression plays a role. So if you're going to write a function for other people to use, not just for you to use, but for other people to use, it's really important that we're very careful about how we use arguments within that function. So if an argument value is not valid, then we have to stop executing that expression and return some sort of error message, because people aren't always going to understand how to use your function. So you need to give them feedback about what is correct or incorrect about their function call. So missing can be used to test whether a value was specified or not. If true, then the value printed is not specified, and if false, then it is specified. This would give you a way to test, did they put in all the arguments they should be putting in? And you could just return a character string saying some of your arguments are missing or something like that. A stop function would stop execution if you come across a certain type of error within the calculation. And this might depend on them putting in the arguments incorrectly. Warning will generate a warning message. So stop obviously will print it. You can specify an error message to be printed. Sometimes warning message are printed and it doesn't mean something's wrong, but you may want the user to know that a certain calculation has occurred, or there's a certain instability in the calculation, or so on. Message will create a diagnostic message. We may get to this or not, I'm not sure. Stop if not. If all the elements are true, then stop is going to be called. And an error message is going to indicate that, something is wrong. So this is just a way to use the stop command, but use it conditionally. Okay, so stop will allow us to provide some sort of error message that would inform the user about what went wrong. And similarly, stop if not does too. It just is a little more efficient coding wise. So let's see how we can use a subset of those to improve our odds ratio function here. So here's all the typical stuff, our cat expression at the end. Then we have out and invisible. So now if we save the results of this function to an object, it will contain a list object that has all of these required results. Once we've finished writing a function, we can save the code to a file. I routinely do this. There's a lot of functions I just use for myself, and I just have them as saved as files so that I can use the source function to read in the contents of the file whenever I need to use it. So using the source is similar to loading a package within R. It just makes that function available. And you don't have to go open find the file, open it, and compile and run it in R. It automatically does that for you. Technically, the code in the file read by source can be any R expression. It doesn't just have to be functions. It could be a bunch of data frames that maybe you want access to at certain points. That would be fine. To avoid specifying the path name, set the working directory for the location of your source file and do that ahead of time. Okay, so here's an example of using it on our odds ratio code. So here we're going to remove, so remember RM removes something, and this is going to remove all of the objects within our environment. Then we call the source function, so this is going to make the odds ratio function available to us. Then we create an X matrix, and then we can run odds ratio on X. Without that command, source odds ratio.r, R would have no way of being able to find or evaluate that odds ratio function. So it's essential for giving R that function definition. Okay, a little bit more about advanced functions here. When you create an object, they're assigned to a particular environment. So think of this as hierarchical, okay? An environment is just a table of assigned object names, but they are hierarchical in nature. At the top level of our environment is the global environment. And objects assigned during an R session are going to be automatically in that global environment. But of course, once we end our R session, that global environment is erased, more or less. Or the ones user created are erased. Assignments within the body of a function use a different environment. It's just at that function level. So let's say we have a function evaluated in R, and there are arguments that are in the global environment. If R cannot find the name of an object locally within that function, it's going to go to the global environment and search for it there. So this can be good or it can be bad because it creates ambiguity, right? If an object within a function has the same name as an object in the global, R is going to choose the object defined in the local if available. It'll default to global when not available, of course. The bottom line here is that objects defined in the global environment are also going to be accessible by the function, and you may be anticipating that or you may not, so it can be dangerous. Let's look at an example. So here we're removing all the objects, just like we did before. And here we're creating a new function, so let's make sure we understand this function. It's called varscope example. It has two objects, x and y, and it's going to do a calculation with x and y and another z. So that's interesting. So where's the z over here? Maybe that's not a very well-defined function, I would say. And then it's going to return an object, the sum of the squares, and it's going to return that w. So let's assign these, because we're using assignment statements within a regular programming environment. These are going to be global values, x, y, and z. But then we call varscope example. And notice we're using different values for x and y here. So before x was 2, now it's 5. Before x was 7, now it's 2. So take a look and make a prediction here. So remember, it's going to look locally for the definitions of the variables x, y, and z, and then it'll go globally if those local definitions are not available. So make a prediction. What will w be? Then take and run this and see what you get. After you run it, notice that w is accessible only within this example. W will not be any value in the global environment unless we assign this function to an object called w, which would be a reasonable thing to do if you want w accessible within the global environment. So when we have vector arguments, this is some really important stuff to know as you get into more advanced R programming. This is day-to-day stuff I use that took me a while to learn only because I never took an R programming course. So I happened upon this just due to necessity more than anything. So functions can perform whole object computation, or what we call vectorized computations, and that usually improves efficiency. I really try to use vectorized calculations whenever I can. Some functions are able to perform vectorized computations without you even having to think about it. For instance, the integrate function will do this. If you have an unvectorized function and you want to apply it to a vector, you could use a for loop. And if you come from other programming languages, I know because I came from R, from having learned a few other programming languages, I immediately started writing for loops every time I wanted to apply a function to a vectorized object. But surprise, in R, that is not the best approach. It's not as efficient as it could be, and it's not as clear as it could be. So other possibilities include the following. We could use lapply, which would apply a function across a list, or sapply, which would apply a function across a vector, or mapply, which is just the multivariate version of mapply, which apply it across elements within multiple vectors. There's also a function vectorize that I use all the time, and this really is just a wrapper for mapply. So it returns a new function. So I'll assign this to a new function, often with a .v at the end, just to remind myself. So if I've written something called brg, then I'll write brg.v, and that'll be the vectorized version of my brg function. And so then I have two functions, one called brg, which just operates on elements, and one called brg.v, which operates on vectors. And that's a really nice way to handle it, because then I have access to both forms of my function. Just because you use these, it doesn't mean you improve efficiency. So we're going to talk a little bit more in the next few slides about how to make sure we do improve efficiency on our function calls in R. So let's start with an example for practicing these vector arguments. These density functions can be passed to a vector, and then we may want to evaluate across a vector type object. So we could write our own Poisson function, okay? And this is just like d Poisson, which would be reasonably a more compact approach because we don't have to write a new function, but again, we could. If we run this Poisson on the vector x 1 to 5 and lambda, our rate parameter, being equal to 1, then we're going to get just that Poisson density evaluated on values 1 up to 5 with a single rate parameter. Okay? Well, what happens if you do this? Take a moment and think about it. It may not do what you think. So maybe when I had first started out programming in R, I would think it would evaluate 1 through 5 for x and at each value of lambda. So I'd get a 1 through 5 evaluated at lambda equal 1, then at lambda equal 2, then at lambda equal 3, 4, and 5. But this is not really what it does. What it does is not actually very useful. What it's going to do is set x equal to 1 and lambda equal to 1. Evaluate that. Then x equals 2, lambda equals 2. Evaluate that. I can't really think, and it goes on until you get x equal 5 and lambda equal to 5. I just can't think of an application where you'd actually want to do that. So what can we do to fix that? Well, we could evaluate the Poisson density for the x values 1 to 5 and for lambda equal 1, 5 by using something like the combination of our Poisson function written up above, or d Poisson, and the sapply. So here we have a column vector where we have lambda.1 equal 1, lambda.5 equal 5. We could add more values for lambda. We could do the whole list, but just for compactness, it's only 2. We're going to run it on the Poisson function, and for x equal 1 to 5. So this will run x equal 1 to 5 for lambda equal 1. Then x equals 1 to 5 for lambda equal 5. Make sure you can make that work. We could do the same thing for the gamma density. Notice we don't call it d gamma because there's already a d gamma in R. But this does the same basic thing. And we could use mapply here to evaluate the gamma density out from 1 to 5 for alpha, beta equal 1, both equal to 1, both equal to 2, or both equal to 3. So this may or may not be what you want to do, but that's how you do it. If you wanted to do it for all possible combinations of alpha, beta, which is usually what I want, you have to use the expand grid.function. Run this and take a look at what parm is. You'll have 1, 1, then 1, 2. 1, 3, then 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. And then it's going to run that gamma density across all possible combinations of alpha and beta and across x equal 1 to 5.